All right, let's start. So far in the study of multivariable functions, we have seen limits, continuity, and then the notion of differentiation, all motivated by the one-dimensional case. We have tried to use the things that we know from the one-dimensional case to understand the theory of the same in the higher dimensional cases. And one of the things that we kept using is the fact that there is not one number like the derivative in the case of one variable functions. It's not just a number that gives the rate of change, but it's actually a vector, which is the gradient. So in if you have f from R to R, roughly the role that f prime plays, if you have some f tilde, let me just call it g. If you have a scalar valued multivariable function, this gradient of g somewhat plays the role of, in some sense, plays the role of this f prime, whatever role f prime plays. And we saw many instances of this when we were trying to calculate critical points. In one variable case, we equate the derivative to be zero. In the multivariable case, we equate the gradient to be zero. In other words, you need each partial derivative to be equal to zero. And then we saw that using the derivative, just like you can get the tangent equation of the tangent line, using the gradient, you can get the equation of the tangent plane or hyperplane in general in n dimensions. So we'll continue the same sort of theme and look at what is the equivalent of the second derivative test. So just to recall, what happens in one dimensions is the following. If f prime is equal to 0, then you have these cases, right? Let me just say f prime at some point x is equal to 0. Then what happens if f prime x is less than 0? And what happens if f double prime x is greater than 0?
In,
And what happens if f double prime x is equal to 0? Can someone recall?
so less than 0, then it will be max. Greater than 0, min. Equal to 0, we cannot conclude anything.
Yeah, inconclusive or saddle point sometimes. So this is, let me just call it inconclusive, sometimes called saddle point also. In the case of higher dimensional or two-dimensional, you will actually see why it's called a saddle point. Now, we would want to do something like this. We would want to look at critical points and classify them. That is the objective. But the thing is, if you have a one variable function, I can, the f prime that I get in turn is a one variable function, right? So f prime is actually a function from R to R itself. And then I can just differentiate this. Again, to get f prime, so what is f double prime? What is the second derivative? It is just the differentiation of the first derivative. Or if you want to write it in terms of this, d by dx of f prime at some point x is nothing but, this is written as this also. You just take this d by dx of d by dx of f of x. Right? So you do twice differentiation and you get another function whenever this is possible to do. But what happens in the case of multivariable functions? You have a vector, you have the gradient vector, but we don't know what it means to differentiate a vector. So in this case, what we will do is we'll look at the components of the gradient vector and then differentiate each of them with respect to each variable. So what we have in the case of multivariable functions is the following. Multivariable scalar valued function. Let me denote it by f. If I have f from Rn to R, it could be some subset of Rn to R also, that doesn't matter much. as long as the point in question is in the interior, that's fine. Now, what is nabla f at the point x tilde? It's a vector whose components are fx1 at x tilde, fx2 at x tilde, and so on up to fxn at x tilde. Right? Each of the components of the gradient of the function are again scalar valued multivariable functions. So each fxi, for example, fx1 is again a function from Rn to R. This had come up, so more generally, I'll just write fxi is a function from Rn to R. This had come up in the discussion in the last session as well. Like we were discussing continuity of the gradient. So similarly, you look at the component functions and you try to get the partial derivatives of these. So if I just consider this fx1 as a scalar valued multivariable function, now again I have x1 up to xn as the variables, right? I can do a dou by dou xj of, let's say, fx1. This j could be anything in 1 to n. This makes sense. This symbol makes sense, correct? Is this clear
Yes, sir.
what this symbol means? I
Sir,
take the first component function and differentiate it with respect to the jth variable.
Yes, it makes sense.
All right. And there's nothing special about the first component function. If I take fxi and take the partial derivative with respect to the jth variable, what I get is, so these are different notations. It could be written as fxi xj, or more commonly fxi xj, or there's also another way of writing it as dou by dou xj of dou f by dou xi. All of these things mean the same thing. Xj, xi. So when you write dou square f by dou xj, dou xi, you're differentiating first with respect to I and then with respect to j. But here it will come out as xi xj, but it's actually dou f by dou xj of dou f by dou xi. Okay, that's all. Just some caution you have to take while you're doing uh, computations. But let's take an example so that we are not just working with symbols blindly. Let me take just 1 minute. Let me take a 3-variable function. Something like x square y square plus z square x plus xyz. Now, what are the partial derivatives of this function? What are these?
2xy square plus z square plus yz.
Yz. And then you have the y variable, which is 2x square y plus just xz. And then you have just 2zx plus xy. These are polynomial functions, so I can just differentiate with respect to one variable and keep all the others constant. So what would fxy be equal to? Fxy at, let's say, xyz. So what do I need to do? I need to take fx and take the partial derivative with respect to y. Now fx is a function again in x, y, and z. I need to differentiate it with respect to y. What
4x
do I get?
plus 1.
This is 4xy plus z, right?
Z.
Is this clear to everyone how we got here?
Yes, sir.
All right. Now with starting with fx, I can differentiate with respect to the same thing again, right? It's once again a function of three variables. So this would be 2y squared.
Yes.
And then fxz would be, I'll stop writing of xyz every time. Fxz is just
2z plus 1.
2z plus y. Now again, starting with y, I can do yx, yy, and yz. Let me just quickly write that down. That's 4x y plus z. Just verify that everything is being computed properly. This is just that, and this is x. And fzx, fzy, fzz. What are these things? You'll have 2z plus y, x, and 2x. Right? You understand these computations, right? It's just successive differentiation, partial differentiation. So in general, if I have a function of n variables, how many, so each of these guys, fxy, fxx, fxz, all of these quantities that we have computed, these are called second order partial derivatives. So it's like you're doing partial derivatives successively two times. So these are called second order partial derivatives. So how many second order partial derivatives are there for a function defined on Rn in general?
N square.
N square, sir.
Yeah. So for, of course, if it exists, there might be some partial derivatives which don't exist. There can be n square second order partial derivatives. So going back to the gradient and comparing it with the derivative of a one variable function, from one number, we got an n component vector. Like instead of a one number, which is the derivative of a one dimensional function, in the case of an n variable function, we got the gradient, which has n components. But the second order derivative is even more, there are even more, right? There, for every variable, you have actually the square number of second order derivatives. So
So,
this, yeah,
can be means at most or for sure.
yeah, it's at most, like some of them need not exist. No?
Zero could also be possible.
Could you repeat that? I couldn't hear you.
Zero could also be a possibility.
Yeah, it could be as difficult to compute. I mean, it could be nowhere differentiable. Well, that's a more technical term. But yeah, it could be zero also. None of the partial derivatives might exist at some point.
So, for a
Yeah.
partial derivative to exist, does the limit have to exist? And does it have to be
Yes.
continuous or only limit?
The limit just has to exist, but the limit now in this case it is we are talking about this limit. The limit as fx you'll have to use. So take for example fxy. This would be what? Limit of fx at your given point x tilde plus something like he2 because y is the second variable minus fx at x tilde divided by h. So this limit needs to exist for fxy to exist.
Sir, in the first time we differentiate,
Yeah.
there also if limit exists, it's a sufficient condition, no, sir. We don't need to check
For
for
the
continuity
existence of
anymore.
the partial derivative, that is enough. Yeah.
All right, sir. Thank you, sir.
Yeah. Continuity of the partial derivative is required when you're talking about things like using the dot product of gradient with the direction to compute direction vector or tangent lines, tangent planes, and all that. For that, you require this additional condition of continuity of the gradient or continuity of the partial derivatives. Right. So even over here, for the existence of the second order partial derivatives, you need this limit to exist. So, for example, if the first order partial derivative itself does not exist, then talking about the second order partial derivative doesn't make sense, right? If fx itself does not exist, then
Yes, sir.
fxy or fxx, all of these things don't exist. So uh, they should exist, and those partial derivatives should once again be differentiable, or this limit should exist. This is a particular case for fxy that I've written down. Similar things you can write for every other xi, xj, you can write it in general. So so the second order partial derivatives, there are n square entries. For first order for first order derivative, you had the gradient which had n entries, and over here you have n square entries. And there is one more thing that we observe, that some of the entries are the same. Right? So there's this and this, they are the same. And then you have this and this to be the same. And what else is same? So this and this is the same. And it's not random that these things are same. You see that this is fxy and this is fyx. That happens to be the same. fxz and fzx is the same. fyz and fzy is the same. So this seems to suggest that at least in some cases, the order in which you perform the second order of derivatives does not matter. Right? If I take fx and then differentiate with respect to y, and if I take fy and then differentiate with respect to x, both of them are turning out to be the same. So
Sir, could you please repeat that?
when, yeah, just one minute. The question that I'm trying to ask is, when is dou square f by dou xi dou xj equal to dou xj dou xi? So what is dou square f by dou xi dou xj? That is, you take f, differentiate it with respect to j first, you take the jth partial derivative, and then you take the ith partial derivative of that. And that is this quantity. But what is this quantity? You take the function f, take its ith partial derivative, and then take the jth partial derivative of that. So you do j first and then I, that is this. You do I first and then j, that is this. So in this example, you see that this happens for everything. So for x and y also it happens, for x and z also it happens, for y and z also it happens. So there is some sort of symmetry, right? The answer to when actually this condition holds is the content of Piero's theorem. So if f is a multivariable function such that the second order partial derivatives exist and are continuous. So here you require that. So if this limit exists, you're just making sure that the second order partial derivative exists. But then again, that fxy, once again, you'll see everywhere over here that each of these second order partial derivatives are also three variable functions, or in general, n variable functions. Then you can talk about their continuity. And if they are continuous, then the order of differentiation does not matter.
Sir, continuous on all points, or any particular point is not
Okay,
continuous, then this will fail.
this is if if it exists and continues at a point, then the second order partial derivatives are equal. The mixed second order partial derivatives are equal at that. So let me just say, if it is continuous at some x tilde, once again I'll be writing Rn. This might as well be some open set in Rn. Then this at x tilde is equal to this at x tilde. So this is a pointwise property, but since it deals with continuity, it will be true in a neighborhood. But you don't need to worry about that. So if it exists and continuous at a given point, then the mixed partial derivatives. So these are called mixed partial derivatives or the second order partial derivatives. The order in which you do the computation doesn't matter. And since these are the example that we took is a polynomial function, you know that the second order partial derivatives exist and are continuous because they are also polynomials. So if you differentiate a polynomial, you'll get a polynomial. If you take partial derivatives of a polynomial, you'll get a polynomial. So in each step, you'll get polynomials. So these are like infinitely differentiable functions, right? You can differentiate them as many times and you'll get, I mean, eventually you'll get zeros because the degree will keep reducing. But okay, even if you don't get that, that's fine. So in this case, you readily see that these are continuous functions, right? These are just polynomial functions. The second order partial derivatives exist and they're continuous and they happen to be equal. So this is just a demonstration of the Clairaut's theorem. For examples where the second order partial derivatives are not continuous, I would request you to take a look at the prof's lectures. There he has given an explicit example.
Sir?
Or even Google it. Yeah.
So, what does this mean by mixed partial derivatives geometrically?
Geometrically, I don't have a good answer to that. I'll think about it and I'll let you know maybe in the next session if there is no more instructive sessions. But yeah, I'll try to get a good answer to that. That's a nice question. Had you asked it in the previous term also?
Yes.
Okay. Yeah. So even then, I probably did not think. Anyway, I'll try to get an answer to that. That's
So this is the
rate of
partial
change of
derivative of the another partial derivative.
yes.
So rate of
So right now I
change of
cannot think of rate of change of
the function.
the change of a function. So it's something like acceleration. So rate of change of velocity is acceleration, right? But then how do you look at the rate of change in some other direction? I do not. I don't have an answer right now. I'll look it up. Yeah.
So
Okay.
last time also I asked whether the converse for this theorem
The converse
is
is not
true
true.
or not.
It's not true. That much I know because this is sufficient conditions. So if the second order partial derivatives exist and are continuous, then this happens. But the converse is not true. This much I have checked check that the converse is not true. Lighter conditions can ensure this. Lighter conditions meaning lesser conditions can ensure this. What is the strongest possible hypothesis under which this condition holds? I don't remember exactly, but this you can Google. There's a Stack Exchange post about only one of the second order derivatives if it exists and continues, then it implies the other one exists and continues. There is something like this. Let me not uh, state something incorrectly, but definitely the converse is not. All right. And anyway, you just need this sufficient statement for this course. I'll note these things down and I'll probably give you an answer this time at least. Yeah, sorry about that.
So one question I had is, this is all leading to finding minimum or a
Yes.
sigma?
Yes. Yes. Yeah. Well, you will not see why this theorem is important because we'll not go into the proof of the procedure, but I'll just hint at why it helps.
Oh,
Right. So yeah. So far what we have seen is the second order partial derivative is the equivalent of the second derivative in the one variable case. And in this case, we have n square of them. And conveniently, this can be placed in a matrix form. So that's the next definition that we will see. Assume there is a function f from Rn to R in the background. The Hessian matrix of a function f, yeah, I'll just write it down anyway. For which, to talk about this Hessian matrix, I need the second order partial derivatives to exist.
So even if one doesn't exist, we cannot talk about this matrix.
Yeah, we cannot. You can say of a function f at a point x tilde, for which all the second order partial derivatives exist at x tilde, is given by well, let's write it compactly first. It's denoted by this h of f. This is a matrix whose ijth entry is actually f xi xt. So if I want to split it out, the Hessian of f, the first entry is x1 x1, x1 x2, and so on up to x1 xn, x2 x1, x2 x2, so on up to x2 xn, xn x1. What am I doing? It should be 1 n. Wait.
So the
N2, this is
column
fine. No?
must be rows and rows must be column.
Oh, am I writing the transpose of the matrix?
I think so.
A11, A12, A1n. No? This is A12. This is fine, I think. Oh, but for the Hessian, it is the other way, is it? Okay. Let me just verify that. ijth entry. Okay. Let me just remark over here. Would be transpose. But it does not matter for our case because we'll be dealing with functions which satisfy the hypothesis of Clairot's theorem. So what happens when Clairot's theorem is satisfied by a function? What can
Symmetric
you say
matrix.
about the Hessian of that function?
So symmetric matrix.
It's a symmetric matrix. So even if you write x2 x1 or x1 x2, it doesn't matter. For example, this and this entry, these will be the same. The diagonal entries will be some x1 x1 x2 x2 and xn x and so on. But on either side of the diagonal, you will have symmetry. That is, by definition, a symmetric matrix. H of f is symmetric if Clairot's theorem is satisfied. Is this clear why this happens?
It looks like both are same also, even if you
No, if the theorem is not satisfied, then
Huh,
you'll have
no,
to be careful with.
talking about the whether it's a transpose or not. They look like it'll always come out to the same thing.
No. Here I'm defining it. No, the HF is either Fxi or Fxj.
Oh,
So in case Claros theorem is not satisfied, then uh, one of them will be correct.
okay.
So
Sir, is there
is
a
the
instance where Claros theorem is not satisfied and the matrix
yes,
exists?
yes, you can have second order derivatives to exist but not continuous. So you can
Okay, sir.
manufacture functions like, so take for example sine square 1 by x and 0. This is in one variable case I'm saying. This is a continuous function. This is a differentiable function as well, but the derivative is not continuous. So similarly, you can probably go to x to the power 4 or something and get twice differentiable functions, but the second order derivative is not continuous. So in one variable case, you cannot talk about Claros theorem because there are no mixed partial derivatives, but you can probably add some function like this and manufacture something like that. Since I don't recollect something from memory, I'll not give you an example.
Got it, sir. I got it, sir. Yeah, just wanted to
Yeah,
confirm. Yes.
yeah. So symmetric matrices have nice properties, and when the Hessian matrix is symmetric, we can do what is called the Hessian test. So next we will look at that. Hessian test.
Sir, just a small query. So in this
Yeah,
one, the HF matrix, so basically which we have taken in this case, since it's a symmetric matrix,
yeah.
so we have taken it this in this order basically, right? Not the transpose just meant to
Not
ask.
the transpose. Let me just verify that. Let me just give me a moment and I'll
Mm,
give you the
sure.
correct one.
Okay.
Do f x2 x1. Yeah, it's actually the other way. This is x2 x1. This is xn x1. This is 1 2. 2 is fine. N2 1n and xn. This is fine. So the ijth entry is not actually fxij, but it is dou square f by dou xi dou xj or f xj xi.
Sir, could you please repeat which is first differentiated, then which is second? I forgot for a second, sir.
So for the ijth entry, we'll do j first and then I, and that is written like this.
Got it, sir. Got it.
So think of this as fxj xi.
Yes, sir. Makes it more clear, sir. Yes, sir.
Yeah. So this is something that, yeah, you have multiple ways of representing the same thing, notations for the same thing. So this order comes because of this interpretation that you take the dou f by dou xi and then do the dou by dou xj of that. That is why here j comes first and then I comes when you're writing, but actually you're differentiating I first and then j. That is because of this. And so for the same thing, you have I coming before j over here and j coming before I over here. But that should not be confusing if you understand why it is written that way.
Yes, sir. Got it, sir. Got it.
Yeah.
So in this case, sir, this comment could be transposed. It's not.
Yeah, I'll remove it.
Okay.
Yeah. This is correct. Hessian test. So the function will satisfy hypothesis of Claros theorem. I'll not keep writing it over and over again. here, right? So we'll have the Hessian as a matrix. Now, you have F prime, F double prime in one-dimensional case. In the multivariable case, you have F, gradient of F, and Hessian of F. These are the equivalent notions, or these are the not equivalent but analogous notions. Now, what is the Hessian test? First, we'll look at it for two variables. Suppose I have a function from R2 to R, or a smaller domain to R, or a subset of R2 to R, which satisfies Clairaut's theorem and all that. You can use the Hessian test and conclude the following at a point A in R2. If the Hessian of F at the point A tilde, now this is a square matrix, right? This is an n cross n, in this case a 2 cross 2 matrix. So if determinant of Hessian of F at the point A, so Hessian of F, the entries are strictly speaking functions, so you evaluate them at a point. So, okay, let me just write the Hessian for this. What is the Hessian for this? This is a 3 cross 3 matrix, which is a Hessian. So you will have 2y square, 2x square, 2x, and this is 4xy plus z, 4xy plus z. Z is 2z plus y. Z plus y. The other one is yz, xx. So you see, this is a matrix of functions. So when you say HF at a point, you actually evaluate it at some point. You can just plug in the values of x, y, z and get the corresponding answer. That's what HF at the point A tilde means. Now, if you compute HFF and plug in some point A tilde in R2, what you will get is a 2 cross 2 matrix with real number entries. You can compute the determinant of that. Now, if the determinant of the Hessian is positive and the first entry is positive, then A tilde is a local minimum. If determinant of HF at the point is positive and the first entry, the leading entry, is negative, then A tilde is a local maximum. Yeah, everywhere is this. If determinant of the Hessian is less than 0, then A tilde is a saddle point. And if determinant is 0, then the test is inconclusive. So there are 4 cases. And not all of them are conclusive. So you'll get an extremum when the determinant is positive only. So when the determinant is positive, you have 2 cases. If fxx is positive and fxx is negative, that corresponds to minimum and maximum respectively. And this you can sort of compare it with the one-dimensional result, where if the second order derivative is positive, then it's a minimum. And if the second order derivative is negative, then it's a maximum. So it's quite similar to that. But here there is an additional condition that the determinant has to be positive. And if the determinant is negative, then A is what is called a saddle point. So I'll just give diagrams of the graph of the function where minima or maxima or saddle points occur. So as you know, okay, first we'll have to have a minima, right? If you have the graph of the function to look something like this, right? So this point is a minimum. And irrespective of what direction you choose to travel on the graph, the function value increases itself. There is no way the function value decreases. This is what is meant by a local minimum. Local minimum. And the local maximum, of course, looks like this. These are intuitively clear what a local minimum and what a local maximum is. Irrespective of what direction I choose to travel along, if I start from a point of maximum, the function value decreases. The height of the graph decreases. So this is what is a local maximum. And what is a saddle point? So a saddle point is something where there are directions in which the function is increasing and there are directions in which the function is decreasing. So what would that look like? That would look something like this. So you have something like this. And let's put it quite far away. So if I have the graph of the function to be something like so if I have the function to be something like this, right? Something like this. So you see what's happening over here? Do you understand this diagram?
Looks like tunnel.
Same, sir.
It's like a parabola which goes a little bit below and then goes above. It's like if it's just a flat thing, there is no change in the height. That's not what I want. I'm going for something where there is a dip and then a rise again. Okay.
Sir, it's more sort of a horse saddle.
Yes, it's exactly like a horse saddle. That is why it's called a saddle point. So
which point would be exactly the saddle point over here?
so take the
Distance
minimum
and
of
direction.
this curve. Okay, or if you want to see it more clearly, let's make it even more curved. Okay? Something like this. And you have this. Right? Now so if you look at this curve, there is a minimum of that curve. No? That's what I've marked on the graph. Now on this point, if I travel into the board, that is in this direction, or behind the board in this direction, you will see that the function value is decreasing. Is that clear?
Yes, sir, yes, got it.
Yes, sir.
But if you travel in this direction,
Yeah, it is
the
increasing.
function value is increasing.
Yes, sir, yes.
So there are points where the rate of change, I mean the function is increasing. There are points of, there are directions in which it is decreasing. So such points are called saddle points. And as rightly pointed out, it is because it looks like a horse saddle. But for minima and maxima, you will not get things like that. With respect to every direction, you will have either increasing in case of minima or decreasing in case of maximum. But unfortunately, this test does not give you a conclusive result every time. If the determinant is 0, then you cannot conclude. Right? Well, that does not mean the point is not a local minimum. So you can have a local minimum for which the determinant of the Hessian is 0. So if this happens, then you're in good shape. But if this does not happen, that does not mean extremum is not attained. All right.
Sir, could you
Now,
repeat your statement, sir? The last one.
So if you compute the Hessian and you see that the determinant of the Hessian is positive and the first entry is positive, then you can conclude that it's a local minimum. But if it is a local minimum, it is not guaranteed that this condition will be satisfied. It might be an inconclusive thing also. If you get this, there is no way to say whether it is a minimum, maximum, or anything else, saddle point.
Sir, we can only do all this if the matrix is symmetric, right, sir?
Yes, that's why for everything we have this blanket assumption that it satisfies the hypothesis of Clairaut's theorem. Once again, I won't go into the proof of it, but I'll just tell you
Yes, sir.
this: if you have symmetric matrices, there are these. You can talk about what is known as positive definiteness, and all of that depends on this being symmetric. You can formulate this using things like eigenvalues, and all of that works. It works well when the matrix is symmetric. All right. So this is the Hessian test for a two-variable function. Here we will not be giving. I don't even know. Yeah, well, there might be a formulation in higher dimensions, but we'll be looking at only functions of 2 or 3 variables. So what was the name of the numbering system? Which was
Sir,
one. This is
here
two.
we can use this for any variable, no, sir, because it's a matrix and we're finding the determinant.
Yes, but this thing is specifically only for 2.
Oh,
This
so the whole
this
method that we studied is only for 2. It's not for anything
yeah.
else.
What I started with this number 1
Oh,
is only for a 2-variable function. Now we'll see
got
what
it.
it is for a 3-variable function. So for f from R3 to R, once again, let's have a point in R3 where Clairaut's theorem is satisfied. We'll assume that the second order partial derivatives exist and are continuous, so that the Hessian matrix that you obtain is a symmetric matrix. Once again, we have 4 cases as before. So I'll first write it down and then I'll give you a way to see it better. So if the first entry or the second order xx derivative is positive, and then this quantity fxx fyy minus fxy square at the point a tilde is positive, and determinant of Hessian of f is positive, this would imply that a is a local minimum. Now, if fx a tilde is negative, the second quantity is positive, this square is just square of the number, and determinant of the Hessian at a tilde is negative. This would imply that a tilde is a local maximum. Now, if fxx, no, okay. If determinant,
Sir, in B case, the debt is less than 0, right? Like,
yeah,
okay.
is not equal to 0 and a, b do not occur, then a tilde is a saddle point. So the only friendly looking guy is this fourth condition, which is similar to the previous case, where if determinant is 0, then test is inconclusive. So let's see what these quantities are, and then we can formulate this.
Excuse me, sir.
Yeah.
The difference between fxy into f ऊपर first a point this fxx into ffy minus xy whole square at the rate a tilde is greater than 0 and determinant of h of f at a is greater than 0. What difference between two
So
conditions?
this is a submatrix. I mean, this is a different. This is a 3x3 matrix, right? There are z ones also. When you're computing the determinant, you'll have fxz, fyz, and so on, right?
Oh, this is one component. This one is first term.
This is yeah. Actually, we'll see that. So when I write the Hessian of A tilde, it's a 3x3 matrix. I'll not write A tilde at every point. fxx, fxy, fxz, fxy, fyy, fyz. Since it's a symmetric matrix, I'm just writing it in whatever order. I'm just using the same thing. Now, what do these conditions say? Is the following. What are the things that you have to compute? One is just fxx, the first entry. You have to look at the first entry. Then you have to look at the determinant of this first 2x2 submatrix. What is the determinant of the first 2x2 submatrix? It is exactly fxx fyy minus fxy square, which is this quantity. And then you have to look at the whole matrix, which is the 3x3 matrix. So starting from the top left, you take a 1x1 matrix and a 2x2 matrix and a 3x3 matrix, namely fxx, fyy minus this, and the whole thing. So you have to compute three determinants in some sense, but since the first one is a 1x1 matrix, it just happens to be just one number. So if you have plus, 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 which is for the 1x1 matrix, you have the determinant to be plus, and for the first 2x2, you have plus, and you have 3x3 determinant also to be plus. This is minimum. This corresponds to minimum. And what does condition B say? If you have minus, plus, minus, then it is maximum. If the determinant is non-zero and it does not follow any of these patterns, it could be minus, 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 or it could be plus, minus, minus, or something like that. As long as it's not plus, 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 or minus, plus, minus, then it happens to be a saddle point. And if the determinant is zero, then anyway, the test is inconclusive.
Could you repeat the from 1x1, 2x2, 3x2? Once again, could you repeat that, sir?
Sir, is
Okay,
0,
so-
0 plus, is it a saddle point? 0, 0 plus.
Let me answer his question first. So,
Sure, sir.
what is the 1x1 submatrix? The first 1x1 submatrix, it is just fxx, right? And then if I look at the 2x2 submatrix, on the top right, it would be fxx, fxy, fxy, fyy. And then you look at the 3x3 submatrix, but the 3x3 submatrix is just the whole thing, because you have a 3x3 matrix itself. So H of f itself is a 3x3 submatrix. So if the determinant of this is plus, if the determinant of this is plus, and the determinant of this is plus, then you have a minimum. If the determinant of this is minus, if you have the determinant of this to be plus, and if you have the determinant of this to be minus, then it is a maximum. Negative.
So it is the metric expansion like that determine when we solve for determinant.
No, it's not exactly. I mean, what do you mean by expansion is not well defined. This is just a way to remember it properly, and it does have meaning if you look at the proof. But if I go into the proof, that will be. I mean, I don't even remember the proof right now, to be frank. And this is just a way of remembering the rules, because these quantities, if you just look at them and try to memorize them, it's not that easy to understand what's going on, right? So one way to look at it is this. That you look at these submatrices, compute their determinants, and look at the pattern of the signs. If you have a plus, 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 you have a minimum. If you have a minus, plus, minus, it's a maximum. And then if you have anything else for which the determinant of the whole thing is non-zero, then it's a saddle point. If the determinant is zero, then the test is inconclusive.
So, sir, 0, 0 plus or 0, 0 minus will be saddle point, sir.
Yes, it will be a saddle point. 0, 0 plus f. What I'm thinking is, can fxx, can both of these be zero? Well, the rule does say that would be zero. I mean
But if
that would be a saddle
existence is
point.
Sir,
there, then
since you have written and, so both of them should occur. Like, if one of them is zero, also the other need not, like, if it is zero or not, also it won't be minimum or maximum, right?
Yeah. So logically, if any of them is zero, also it will be a saddle point. That is there. But I'm thinking, are there functions for which the first two are zero and the whole determinant is non-zero? Yeah. Once again, I cannot quickly come up with an answer for that. But well, the rules over here do say that it would be a saddle point. If such a thing were to occur, it's a saddle point.
got it, sir. Got it.
But does that actually occur? I'm not sure.
Got it, sir.
Because over here, you see, in a two variable case, you cannot have this to be positive and this to be zero. So there is this one case we have avoided, which is determinant is positive and fxx is zero. That cannot happen. Why cannot that happen?
Sir, could
We
you
have
repeat
dealt
the
with
question?
grid. We
Because
have
the first element only will, okay, sorry. No. Please continue, sir.
yeah. So if determinant is positive and fxx is equal to zero, what is the thing then? We have not covered every case. It seems like, right? So the question is,
Yes.
what if determinant hf is greater than zero and fxx is equal to zero? Does this fall under any of these cases?
Saddle?
No.
No.
For saddle, we are saying that if the determinant is negative. So I'm saying determinant is positive, but fxx is zero.
Okay.
Sir, you just mentioned this is not possible. Why would that be, sir?
Yeah.
Sir,
So I'm trying to motivate.
shouldn't it fall under determinant not equal to zero?
There is determinant not equal to zero in the ABCD case. So this is I'm back to the two variable case just to clarify something which
Yes, sir. Because the multiplication of the diagonal should be is kind of like if we multiply all the diagonal elements, we'll get. Is that incorrect? Then we'll get
it's
zero,
not
no, sir.
that
It's
complicated.
not.
So if you have a matrix of this form, you will have zero something over here. Okay, let me just call this guy as D. And since this is a symmetric matrix, I'll have C and C, correct?
Yes,
If
sir.
fxx is zero, then what would the determinant be?
Always negative.
Minus C square.
Minus C square. So then determinant will never be positive. So you cannot have a determinant positive Hessian with fxx equal to zero in the 2 cross 2 case.
Right, sir. Got it.
Got it? So similar things may happen over here. I cannot immediately see that if fxx is equal to zero, does it force certain things? So in this case, you see it forces, if fxx is equal to zero, it forces determinant to be negative or at least non-positive.
Sir, what if C is zero?
Yeah, non-positive. That's why I corrected it to be non-positive.
Okay, sir. Got it.
It's minus C square in general. If C is zero, it will be zero. So similar things may happen over here, but well, the rule dictates that as long as determinant is non-zero and A and B do not occur, then it's a saddle point. Is that fine?
Yes, sir.
Okay, so let's take our familiar example of f of xy is equal to 1 minus x square minus y square. So do you remember what the graph of this looked like?
So some kind of opposite parabolic cone.
Well, you can just call it a hill-like curve. It's like this. And this is what the graph would look like. So if I look at this x, y, z, this would be at a height 1. So at the origin, what do you expect the behavior to be? What would the origin be?
Maximum, sir.
Maximum.
So it's a
Global
local
maximum.
maximum, right? It's actually a global maximum, but Hessian test can only detect local maxima. So let's do the Hessian test and actually verify that. So first we'll have to calculate what the critical points are. And in order to calculate the critical points, I need to calculate the partial derivatives. In this case, it happens to be just minus 2x minus 2y. So nabla f at xy, if it is equal to 0, this would imply that xy is the origin. There's no other choice, right? I'm not writing everything out explicitly, but this is clear, no?
Yes, sir.
Yes, sir.
Right. So I just need to compute the Hessian at the origin. Now, what is the Hessian? In order to do that, I need fxx. In this case, it's minus 2. fxy, which is 0. And fyy, which is again minus 2. So what's the Hessian?
Sir, 1 second, sir. The above statement which you just wrote, that you're just finding the critical point, no, sir?
Yes, this is the only critical point.
Right, sir. Got it.
Because we need to, okay. Yeah, that actually highlights a sort of a major error that we have said is a critical point. So at critical points, we do all of these things.
Sir, so even for the 3x3 also, it's a critical point, right?
Yeah. So you do analysis of maxima, minima at critical points, right? That is nabla f at a tilde is 0. Same thing over here. Even in the one variable case, you look at points where the derivative vanishes and then look at the second derivative at those points. You just don't do it for arbitrary points. So in general, the HF would be minus 2, 0, 0, minus 2. Here, the functions are constant functions. So plugging in 0, 0 or whatever, it will give you the same Hessian matrix. So in particular, at the origin also, this is the Hessian matrix. Now, under which case does it fall? To do that, what do I need to do? I need to look at this guy, determinant of Hessian at 0, 0. That's plus 4. So this is positive. And fxx at 0, 0, the leading entry, that's minus 2. And that is negative. So what happens when you have a negative positive or positive negative?
I think maximum, sir. Yes, maximum, definitely.
Is a maximum. Oh, and by the way, this 1 cross 1 submatrix, 1 cross 2, 2 cross 2 submatrix and 3 cross 3 submatrix, this works over here also. To remember the conditions, if you look at this, where should I write it? I'll write it over here. So here you have fxx, fxy, fxy, fyy. And if you take this, the 1 cross 1 submatrix and the 2 cross 2 submatrix, you have only these two cases, right? So plus plus will be minimum, plus minus will be maximum. So similarly, over here, plus 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 is minimum. So if you have all pluses, you'll have minimum. And you have alternating plus and minus, you'll have a maximum.
You mean to say the signs?
The signs of the determinants of the 1 cross 1 matrix, 2 cross 2 matrix, and so on. This is arguably simpler way to remember.
So this is just a shortcut, sir, what you just wrote, no? just to remember.
It's a shortcut, yeah. You can
Yes,
Sir,
think of it that way.
sir, here determinant is not negative for 2 cross 2, right?
Right. Yeah, there's that catch that it is not. In this case, you have determinant positive and sub cases. Here you have cases where determinant is negative also in the 3 cross. So what is the sign convention you have to sort of memorize?
No, sir, you have written for 2 cross 2 plus minus, right? It should be minus plus, right?
Yes, sir.
Oh, right. Yeah. Okay. This is correct. Yeah. Sorry. Yeah. 1 cross 1 should be negative and the determinant should be positive. Right. So, okay, back to the specific example. We see that 0 is a maximum by this argument, and this was a easy example. You can consider other functions and do 3 variables if you want and verify what happens in those cases. You can take sine and cos functions and combinations of that, and you will see that it can have infinitely many critical points also, because cos function and sine function. Let's try to see that. Now f of xy is cos x plus sine y. Will this be an easy? I'll just take something like y cos x. I'm just making my life easier. What is fx? This is minus y sine x. I don't think I'll get infinitely many. Let's do this now. Okay, sorry about this. Sine of x square plus y square. This will definitely work for what I want to demonstrate. So where do you expect minima and maxima for this? Before we go about the Hessian test, what do you feel like when you look
0,
at the
0,
function?
0, 0.
But at 0, the function value is 0. No?
Oh, it's just like a saddle point, I guess. I don't know. Sorry. Or maybe when y is equal to x.
Even if y is equal to x, if y is equal to x is equal to 1, then you have sine 2 or something. What is the maximum value of sine?
One.
1.
1. Sorry.
1. So where is 1 achieved?
Okay, circle of
When
radius.
y,
By 2,
x
pi by
square
2.
So
plus
if you have x square plus y square is equal to something
pi.
like 2n plus 1 pi by 2 or 2k plus 1 pi by 2. I expect a max over here. This is just guesswork. Huh? This is just to understand. And where do I expect
Minus
2k minus 1? No, wait, what?
minus pi by 2. The 2k plus 1 minus pi by 2. I
No,
think
but
so.
that won't work. Okay, we have the argument to only go to positive ones.
Oh, yes, sir. Yes. Pi, I forgot, sir.
Wait, this is
Minus 3 pi by
2k
2.
pi plus pi by 2. Minus 3 pi by 2 won't work because x square plus y square will never be negative.
Okay.
So it's actually
I
4k
think
plus
pi,
1
sir.
pi
I
by
think
2
pi.
and it's 4k minus 1, or I can just write it as 2k minus pi by 2, and this I expect to be a minimum. Here k varies in, it starts from 1, 2, so on. It doesn't take all integer values. Well, over here it could be 0 also. So there's definitely a better way of writing it. So here k is equal to 0 is also permitted. But let's see. These are all guesses that we are trying to do. And let's realize this using the Hessian test. So what happens to fx? I'm skipping steps, but I'm just writing the thing which is fairly easy to compute. Fy is just 2y times cos of x square plus y square. And what's the Hessian matrix? Okay, let's do the fxx also. Fxx is 2 times cos square plus y square minus 4x. If I make some mistake, you just let me know, right?
It's a 4x square, no?
You will get a 4x and an x, yeah. So this is relatively easier. This is minus 4xy.
Sir, how 4x square?
Just one moment. So when I'm differentiating this again with respect to x, I'll have to use a product rule. No, I'll have to
So
first
plus,
Okay, yes, I get it, sir. 2x into 2x.
so
yeah, there's a
plus y
2x, and
minus
then because
minus
cos is
cos square.
minus sign, right?
Sorry. Yes.
Cos becomes minus sign.
Sorry.
All of this you can
Sorry.
verify.
Got it, sir.
This is like product rule. So here you don't need to do the product because x is a constant when you're differentiating with respect to y. So here you'll get a symmetric sort of solution. You replace x with y and you should get the answer. So it should just be this. Now the Hessian matrix in general looks scary, but first of all, we don't need to compute the Hessian matrix in general. All we need to do is at critical points, right? What are the critical points? So I need fx equal to 0, which is 2x times cos of x square plus y square is equal to 0, and fy is equal to 0, which is 2y times cos of x square plus y square. This is equal to 0. So what are all the points which set? I can forget about the 2. That's a constant. So either I have xy is equal to 0, 0, 0, or x square plus y square
2, 1. Oh, sorry. Equal to
is equal to some
0.
k pi plus pi by 2.
Yes.
Right? Do you see this? These are all the critical points.
Yes, sir.
Sir, could you
So the
explain
first,
k pi plus pi by 2 once?
so if you have k pi plus pi by 2, where k is some integer. So let's take it to be, so k is any integer in 0, 1, 2, so on. Right? So if I have 0, for example, x square plus y square is pi by 2. Now, if x square plus y square is pi by 2, then I'll have this quantity, cos of x square plus y square, to be 0.
Yes, sir.
And that appears over here also. Right?
I understood
If,
it, sir. So it
yeah,
will be in
if
multiples of pi by 2 only, all the time.
pi by 2, well, not, it'll be odd multiples of pi by 2. It cannot be pi, for example. Pi is also a multiple of
Yes,
pi by 2,
sir.
but
Only pi by 2 will be coming.
pi
270
by
or
2, 3 pi
90.
by 2, 5 pi by 2, and so on.
Yes, sir. 90 or 270 only. Okay, yes, sir.
90, 270, and then 2 pi, you can keep adding 2 pi to them, multiples of 2 pi to them, and
Yes,
it'll
sir.
not change.
Understood, sir.
So, and there is this another guy, 0, 0, and there are these guys. So, let's take those two cases. So the first one is xy is equal to 0, 0. Now, what is the Hessian matrix in this case? I won't write hf of 0, 0. Now, if I plug it in, can you guys tell me what happens at 0, 0? Plug the value x equal to 0, y is equal to 0 in these three quantities and tell me what the Hessian is.
First one will be 2.
2 cos x square plus y square.
Yes, sir. First one is 2.
Second is 0.
Yes.
0 again. 2 again.
So this is again 2, right?
Yes.
So what does the Hessian test say?
Minimum.
Minimum, sir. Plus, minimum.
So this is minimum. What is the function value at 0, 0?
Sir, could you show the function?
0.
It is sine of x square plus y square.
0.
Yes, 0.
0.
So this is 0. So this is something sort of unexpected, right? The minimum value of the sine function is not 0, but yet this Hessian test is telling me that this is a minimum. So this is one more cautionary demonstration that it detects only local minima. All right. So
Sir, but for x square plus y square, the minimum value is only 0, right? Since you said -1 couldn't be 0. Sorry, minimum.
-1
Then-
can be the minimum. No, x square plus y square can go to something like 3 pi by 2. x square plus y square itself cannot go negative, but the sign of that could go negative. Sine of 3 pi by 2 is minus 1. So I'm calculating the minimum of this function. If I take x is equal to square root of 3 pi by 2 and y is equal to 0, what is the value of the function?
Okay, it's -1.
Right.
Yes,
So
sir.
the sinusoidal wave, as you are in the positive argument, also you will get negative values. That is
Yes,
there.
sir.
So
Okay.
if you draw this
Understood, sir.
graph of the sine function, something like this, you have these points in the positive side of the x-axis also where the function value is negative. Okay, so the minimum and maximum of sine are +1 and -1, and these are attained at infinitely many points. But here, the function value happens to be 0, and the Hessian test is saying that it's a minimum. So why does this happen? I would strongly suggest this exercise. Visualize this on GeoGebra or any graphing software that you have. Just plot the graph of this and observe what happens. This is a good fun exercise.
Sir, at the point it will be something like a downward hill, I'm guessing.
Yeah, it'll be a valley. Yeah,
Valley,
it will
downward.
be a
Okay,
valley. So it does not go all the way down to -1, but since the argument itself does not go beyond that, at that point it becomes a valley. That I cannot explain it in words better than that. So this is
Right,
what you
sir.
have
Got
to
it.
do.
Got it.
And just visualizing this, the graph of this function is also, it will tell you the behavior of the function. It looks like ripples away from the origin. So you will see multiple minima and maximum as is to be expected. So the second case is that of x square plus y square is equal to k pi plus pi by 2. So what is the Hessian in this case?
Two cos x square plus y square.
-2 minus plus -4. So what will be x square then?
Putting the value of x.
Right, you'll have to know what x square is.
Yes.
Keep x square as it is.
So it will be -2 minus 4x square.
No, this will be 0, right?
Oh yes sir, yes sir.
Cos
Because
of x square plus y square
odd
will be,
multiple of pi by 2, right? Sir?
it's odd multiples of pi by 2.
Yes.
But depending on whether it is pi by 2, I mean, things of the form 4k plus 1 pi by 2 or 4k minus 1 pi by 2, this factor will change. So let us do it instead of doing it for the general k pi plus pi by 2. Even that can be worked out in terms of -1 to the k and all that. Let's just take two examples. X square plus y square is equal to pi by 2. And so this is sub cases. This is like 2a. X square plus y square is equal to pi by 2. In this case, what is the Hessian? Keep x and y as it is if you require to use x and y. So this part becomes 0. This part becomes 1. So it becomes a -4x square. Correct?
Yes sir.
And this? Again, -4xy.
Y. Yes, -4x.
And this is -4y square.
Yes.
So this is minus
4x.
4x square minus 4xy minus 4xy
Oh,
minus
-4y.
4y square. So we have not taken specific values of x square and y square or x and y, but I'm just saying that for any x and y that satisfies x square plus y square is equal to pi by 2, there are infinitely many of them. But for any of those values, what happens to the determinant of this?
0.
Yes.
0.
Determinant of HFF is 0. So the Hessian test is inconclusive, but actually, by very evident properties of the sine function that you already know, that you know that this is a maximum. right? If I put x square plus y square equal to pi by 2, I'll get sine of pi by 2, which is 1. Sine function cannot go beyond that anyway. So in this case, the Hessian test does not conclude this, but actually this is a local minimum. Sorry, local maximum. But Hessian test fails. So this is what I was saying, that you can have points of maximum where Hessian test fails or is inconclusive. Both are the same thing.
So can you repeat this point again, please?
Just one. I'll just give this point root pi by 2 comma 0 is max. So you know the fact, what I'm saying is the Hessian test fails. So it fails to tell you that it's a maximum, but I know that this is actually a maximum, because if I put x square plus y square is equal to pi by 2 in the function expression, then I get sine of pi by 2, which is 1, and the function can never go beyond that. It is sine of something. Sine of something is at best 1 or at maximum 1 and a minimum of minus 1. So for example, the point root pi by 2 comma 0 should have been a maximum. It is a maximum, but the Hessian test does not detect that. So this is just an example where the Hessian test fails. Or by fails, I mean it is inconclusive. It is better to say Hessian test is inconclusive. But actually, this is a maximum. Any point on the circle x square plus y square equal to pi by 2 is a maximum. You can do the same thing for other points, and you will see that this happens in every 4k plus 1 pi by 2 and 4k minus 1 pi by 2. Everywhere else, you'll get minus 1 instead of plus 1. So you'll get 4x square, 4xy, 4xy, 4y square. All right.
Yes, sir.
So this is about the Hessian test.
Sir, these are a few exceptions.
Well, this can happen, is what I'm saying. It's not exactly an exception. We have covered this in our rules, right? If the determinant is 0, okay, we are in the two-dimensional case. We do say that the test is inconclusive. We are not. So what I would call an exception is there is this rule, but it does not work in some conditions. But in our rules, we have included that case also. So this is not technically an exception, but it's one of the cases.
Yes, sir.
All right. So that's that.
So it's not an exception, but you at that point it is a maximum, but according to the rule, we can't say through Hessian test it's a maximum. It just
why
gave
could
up.
we say that? Yeah. Why could we say that it's actually a maximum? Because we know something about the sine function. What if it was some complicated function that we did not know anything about, or it is not very easy to see that this cannot attain something more than that. So in that case, we will need something else, if even there is something else to analyze the behavior of that critical point. Okay.
Got it, sir. Yes, sir.
Yeah. So the last topic is differentiability of something like this, of a multivariable function. Now we have talked about partial derivatives, directional derivatives, but we have not said what it means for a function to be differentiable. We have said that its first order partial derivatives exist or second order partial derivatives exist, but we have never said that the function is differentiable. In a one-dimensional case, those were not separate notions. Right? There's just one differentiation that you can do. There's only one variable, and if you differentiate, that would be partial derivative or the total derivative, or it doesn't really make a difference. But in multiple variables, there is a notion of differentiating only with respect to one variable, and then there is this notion of differentiability. It's a technical thing which is there mostly only for completion. And there are certain things which are equivalent. I'll state both of them. And it's not something that you need to care very much about. So in one-dimensional case, when is a function said to be differentiable?
Smooth
What is
and
the first
continuous
principle
line.
definition?
Or derivative exists, limit exists.
Yes. Yeah. So you need this limit as h goes to 0 of f of x plus h minus f of x by h. This you want the limit to be you want the limit to exist, and here there is no HEI or H U unit direction. There's nothing like that because there's you can just add these real numbers. X is a real number, H is a real number. You just add it and measure the rate of change of the function with respect to the input, and you call that the derivative. So this is just like the speed of the function. Now, if I rearrange this, what do I get? I'm just rearranging this, taking it inside the limit and just writing this. Is this clear that this is the same as this? Is it fine?
Yes, sir.
I've just
So
taken
you
f
just
prime to,
multiply.
yeah, I just multiplied by h and took it to the other side and then brought it inside the limit because it does not depend on h. So that's all I did. Now, if I were to use this definition for differentiability, replacing this, there are a few problems. First of all, I don't know what f prime x times h would be, right? In this case, this is a real number, this is a real number. I can just multiply them and I'll get a real number. But in the multivariable case, this is not a real number. So I would replace this with gradient. But what does gradient times a real number mean? That doesn't make sense. So since gradient is a vector and we know how to multiply vectors, I can replace this with h being a vector. But then the denominator would not make sense. I cannot divide by a vector. So the correct formulation in higher dimensions is now f is from Rn to R is said to be differentiable at, let's say, a point A if limit as h goes to 0. Now this h is not a scalar. Now h is a vector. You know how to take limits along vectors. And I can add two vectors, right? Now h, let me just put a tilde under the h to emphasize that this is a vector. Instead of f prime x, I'll just have nabla f at x tilde dot product with h tilde. So far, so good. All of these symbols make sense and they are a direct analog of the one-dimensional case. But then I have to divide now. Divide by, I cannot do h or h tilde because that's a vector. So we take norm of that if this happens. So this is the definition of differentiability of a scalar valued multivariable function. First of all, the partial derivatives have to exist and the gradient has to satisfy this equation, which means that this limit exists and is equal to 0. The limit of f of x tilde plus h tilde minus f of x tilde minus gradient dot with h tilde divided by the norm of h tilde. So it is a direct generalization of this, making obvious necessary changes so that all the quantities make sense. All right, so this is when a function is said to be differentiable. Even though this is the definition, it is not very practical, correct? It's not, you cannot, checking whether this condition is satisfied is not easy all the time. Just like when we defined partial derivatives, we said that if the limit exists and all that, but then we, to compute it, actually, we used certain other techniques. So similarly, if you want to check something is differentiable, well, this would be the foolproof way, but there are certain other equivalent conditions which you can use. Which I'll list over here. F is differentiable at a tilde. This is the same as saying if and only if, or equivalently, tangent hyperplane. I'll just write it as tangent plane.
So this A tilde is any point, right?
Is at any point, yeah. In the domain, well, strictly speaking, again, this could be some open set in that, and this could be the interior of that. Tangent plane at A tilde exists. Well, tangent plane is also the same as best linear approximation. I probably did not mention this in the session. This tangent plane is also known as best linear approximation. At it exists.
Sir, but if the tangent plane has a slope of that does not exist, meaning it's perpendicular, then it would not be differentiable, no, sir?
You mean you have a function for which the tangent plane looks like this?
Yes, yes, sir. At
Exact-
least in one dimensional, it was like that, no, sir. The tangent is like perpendicular to the x-axis. It is not differentiable.
Well, tangent can never be perpendicular to the x-axis. Right? Then you have a point of
Like a saddle
non-regular.
point kind of thing. I um,
No. So if something becomes vertical, if it goes like this, then this is no longer a function, right?
It's
So
undefined.
oh yes, yes, sir. Yeah, yes.
right, and if you have something like this, then even over here in this section, at given point you have many values for the function. So you cannot have a vertical tangent line.
Tangent makes sense, sir. Then it violates the definition. Got it, sir.
Similarly, you cannot have a vertical tangent plane.
Got
And
it,
if
sir.
you remember,
Got it, sir.
when you have the existence and continuity of the partial derivatives, your tangent plane is given by z is equal to f of x naught y naught plus something. I think it was something like nabla f dot x minus x0 y minus y0, something like this. This can never be vertical. You see, a vertical thing would be something like ax plus by is equal to 0 or b.
Yes,
If you
sir.
have a
Got it, sir.
vertical plane, that would
Then
be of this form.
got it, sir. Yes, sir. Zero is equal. Yes, sir.
So, but
Makes
in this case, the coefficient of z cannot be mid zero, at least under reasonable regularity conditions, which is partial derivatives exist and are continuous.
got
So
it, sir. Yes, sir.
there you can have maybe something like x to the power 1 by 3, and all these things are not well defined. Well, okay, there might be a clause of regularity, but if the tangent plane exists in the case of nice enough functions, by nice enough I mean existence of partial derivatives and continuity, then in that case the tangent plane will exist. In that case, it will be differentiable. So these two are equivalent formulations, and just to tell you one of the examples, if I take, let's say, a function xy, which is f of xy is
Sir, yeah, sorry to interrupt. Sir, so
One
when
moment, one moment.
yeah, sure.
Let me just call this guy mod x. Is this differentiable at the origin? Or what are the points where this is
No, sir.
differentiable?
No, sir. No, sir.
So what would the graph of this function look like?
It's like a
Any
folded
idea?
A
paper,
sharp
sir.
edge,
Folded paper.
a pyramid, folded pyramid, I guess, sir.
So there is no change in the y direction, right? And in x direction, it looks like mod x. So you will have something like, if you can understand what I'm trying to draw, it will be something like this. That is in the xz plane, and the same thing carries on in the y direction. So it's something like this. You see that?
Yes, sir.
Let's try to make straight lines. Something like this. Something like this. So it's like this and this. So it's like a mod x on the xz plane, which is extended in the y direction as it is. Think of it that way. Now, at the points on the y-axis, at any point on the y-axis, does the tangent plane exist?
No, sir.
Because there's a sharp edge, right? At such a thing, you cannot have one tangent plane. So you can verify this by actually trying to come up with the partial derivatives, and you'll see that the partial derivatives will not be continuous, so the tangent plane doesn't exist and so on. But even just by looking at the graph, you will see that at the points where there is a sharp edge. Yeah.
Sir, I want to ask one thing. I just missed the plot. So exactly what is the topic is?
This is differentiability of a function, and we just said that differentiability of a function is equivalent to the existence of a tangent plane. Differentiability at a point is equivalent to existence of tangent plane at a point. And through this example, I'm just trying to say that sometimes just by looking at the graph, you can say that it is not differentiable at that point. So the points on the y-axis where the fold happens, if you want to look at it that way, you will see that there is no tangent plane. Because to have a plane, there should be some sort of smoothness. Whenever there is a sharp edge, there is no tangent plane there. So on such points, the tangent plane doesn't exist. It implies f is not differentiable. But on other points, the tangent planes exist. So and on those points, the differentiability will be valid.
So rather than saying the tangent plane doesn't exist, can't we say infinitely many tangent planes exist?
No, I would say the tangent plane doesn't exist. Yeah, I mean, yeah, okay, that's one way to look at it. When there is a sharp edge, it's like it is turning infinitely fast. That is what you're trying to go for, right?
Yes, sir.
Yeah, so you can put any plane and it will go tangent to it.
Yes,
But the way I interpret tangent planes is all possible velocities of curves through that point, which is way past the scope of this course. So, okay, in whichever way you want to look at it, the tangent plane, well, then this statement, there would be a problem, because if you say that there are infinitely many tangent planes, then you're saying that the tangent plane does exist. Then
yes,
you'll
sir.
have
Got your
to
point. Got your point.
you have to say that a unique tangent plane exists or something like that. So, but yeah, hopefully the point has come across clearly that uh, the tangent plane, as we have seen earlier, if it exists, then differentiability is guaranteed, and vice versa. It's an equivalent statement. So in such examples, you can actually verify that. And this would also mean another thing: differentiability implies continuity. So differentiate this is not part of this example. So let's just write it separately. Differentiable implies continuous. So I'll just write it in short here. So if you have a discontinuous function, then there is no way it is differentiable. So I think the function was this xy divided by x square plus y square. Was it this? Probably this one. This is for xy not equal to 0, 0.
Yes, sir.
And
This is the
0.
function.
This is a very classical example of a function. So if you want to say that this is not differentiable, you can just look at, instead of trying to plot it and seeing tangent plane exists or not, another way to look at it is you put y is equal to x, y is equal to minus x, you will get different limits. And then you can say that it is not continuous at the origin, so it's not differentiable at the origin. And as an exercise, you can actually look at the graph and try to see that why the tangent plane does not exist. Visualize f and check that tangent plane does not exist at the origin.
So this is an example where it's continuous but not differentiable.
No, this is not continuous. That is why it's not differentiable.
Oh.
So differentiable implies continuous. So this is actually an example where it is continuous but not differentiable.
Yes, sir.
So here, continuity itself is a problem. So differentiability is impossible.
Got it, sir. My mistake, sir.
Sir, if any function is not continuous, then it will be not differentiable as well.
Yes. So the statement A implies B is equivalent to my negation of B implies negation of A. If you don't understand this logic, it's fine. So if something is differentiable, then it is continuous. Is equivalent to saying not continuous implies not differentiable.
Is there any function that is not differentiable but continuous? Like
That's
the earlier
this.
case?
That's an example. You can, in fact, just take any function and make it sharp. You can draw sharp diagrams however you want, and those will be continuous. Continuous means what? Like, how do you understand continuity? Continuity is that there are no jumps, or the points close in the domain will go to close points in the range. So there are no abrupt jumps and so on. So
we
for
just
that,
have to look at the sharp edges.
Sorry.
Could you please explain us what is the sharp edges denote? Like if they are not differentiable.
In the graph of the function. Okay. In the graph of the function, if you have things like this, that's a sharp edge in the sense that sharp edge is exactly what you would think it would be. So the graph of a function being smooth and being sharp just means that, well, I could explain it again in terms of the tangent plane not existing, or is there a better way to say? Yeah, I guess that is how I would explain the tangent plane, or if you try to draw tangent lines.
One more example, if it is not, it is only a mod x function types. We just have to denote it with a mod x or any more.
Not necessarily mod x. You can.
Piecewise also will become sharp now sometimes.
If you take a cone, so this has actually exactly one point where there is sharpness, which is the origin. So for the cone, everything else is smooth. This you can look at as square root of x square plus y square. If you plot this, you will see that this happens. And when you actually do the computations, you will see that when you try to calculate derivatives, you will have this 1 by square root of x square plus y square times something. So this times 2x. The partial derivatives will have this 1 by square root of x square plus y square, which will cause only problems at the origin. I'm not giving you all of the details, but you can
Understood, sir. Understood very well. But one thing, if it is not differentiable, then the answer would be what? If any function was given, then we have to just check the function is non-differential. Then what will be the calculated value is?
If you are asked whether something is differentiable or not, it will be simple to verify using either of this, is what I'm saying. That you can either draw the graph easily and see that the tangent plane does not exist, or it will not be continuous in the first place. Because
non-differential, sir. Non-differential. I am asking, sir. Non-differential. What like if something is non-differentiable means it's denoting 2, 0, 0.
No, I didn't get your question. Could you repeat?
If any function was given, say x square, if this function is non-differentiable, then how non-differentiable? How means what is the denotion to it?
So this is the equivalent formulation. You talk about differentiability at a point. So at that point, if you can verify that the tangent plane does not exist by quickly drawing up a diagram, or if you can prove in some way that at that point continuity fails, these are two ways to establish that it is not differentiable. And the questions that you will be asked will not be more than this. If you want to be absolutely sure, then you'll have to deal with this definition, which says that the following limit exists and is equal to 0, which is a direct generalization of the one-dimensional case. So this is the principled way of doing this. This, for most cases, will be sufficient. All right.
Sir, I have a small doubt on limits of a multivariable function. Can I ask now, sir?
Let us take the doubts for this session first. So yeah, the
All right.
subject matter is done. If anyone has doubts, please speak up. If you don't have doubts, feel free to leave.
Thank you so much, sir.
Okay, there doesn't seem to be doubts for this
Sir,
session.
just a second.
Okay.
So I just wanted to. So in case differentiability of any multivariable function at any point exists, so by default we can say that the partial derivative exists, right?
Differentiability implies existence of partial derivatives is true. Yes.
Okay.
So it's kind of implicit in this definition. So f is said to be differentiable if this limit exists. For the limit to exist, first of all, this gradient should exist. So strictly, if you want to write it even more rigorously, you'll have to say f is said to be differentiable at a if the gradient exists and this limit exists and is equal to 0. So differentiability implies existence of gradient.
So this h, so in one instance we'll take it as h comma 0, and another instance we'll take it as 0 comma h, right, sir?
No, this h is a vector. So
Right. Sorry,
if you are talking about two variables, this x tilde could be over here. Oh wait, no one pointed this out.
Okay.
Okay, so you have this point a tilde over here, and you are taking h tilde going to 0, meaning a tilde plus h will be going to a tilde. So you know how to evaluate limits. So this is like saying limit as xy goes to 0,
Correct.
0 of, let's say, for this thing, if you get something like this.
Right.
So this would be 1, correct? So it's not that you're taking h tilde to be 0, 0 or 1, 0 and then doing it. You're taking all possible routes to 0.
Okay. No, actually, I got this, what you're saying, but I was just talking with respect to this formula which you
Yeah,
showed
for the
here.
formula also, this H tilde, in the two-dimensional case, what would H tilde be? It would just be H1, H2 going to 0, 0.
Correct, correct, correct.
So this is like a function in two variables. This is exactly like this. This is just a specific example. So you'll
So
have to take
basically, in this
H1,
one,
H2
you
going to 0,
think
0.
H tilde will be H1 and H2 basically.
Yes, H tilde will be just some H1, H2. In general, H1, H2 up to Hn.
Okay.
And in order to say that this limit exists, you have to say that the limit along every curve exists, or and this is also actually 0 tilde to be frank. So this goes to the 0 vector.
So this is
And to
basically
say
like a super test, right? So it will include
yes,
everything. So
yes, yes.
it will tell
Typically,
us
things
like
which are
something.
given in limit exists or this thing, that is the first principles definition. And then, and most of the time, those will not be very easy to work with. Like the
Okay.
workable definition will be something else, or
This
sometimes
question
there will be not
says
equivalent. Could you please mark? Okay, yeah. There you have to use some sufficient conditions. So, for example, continuity is a necessary condition.
Right.
So,
For differentiability.
for differentiability. Yeah. So this is an equivalent condition. Tangent planarity exists. So all of these things are
Okay. For continuity, if we immediately find the limit is not equal or does not exist, then
yes,
at that point only we can say that it's not differentiable. Yes.
it's not differentiable. Yeah.
sir, if this differentiable at B, then if the question says it is not at A tilde, it was differentiable at B tilde, then the answer would be like F, wherever the A tilde is B, na? It's just a point. They are denoting a point, na?
Yes, it's an arbitrary point.
Any point can be given to it.
Yeah.
Okay.
All right then. The other limits
So,
questions I'll take.
it's a very quick question, sir. So
Yeah.
suppose if there's a limit x comma 0 tends to 0 comma 0.
X comma y goes to 0, 0.
Sorry, x comma y is equal tends to 0 0, and the function is xy by xy.
Xy by
Can
xy.
we? Yes, sir. That's it. This
This
is
is
something.
one.
Yeah, this is one, sir.
Yeah.
So whenever we can cancel out something like this,
Yes.
we can reasonably calculate the limit like this, no, sir? Is it like?
Yeah. So if you have something like limit as x goes to, let's say, 1 of what do I want? X squared minus 3x plus 2 divided by x minus 1. How would you do this? In the one-dimensional case, what would you do?
We would simplify it because we don't want to see where it doesn't exist.
Yeah,
Like
so the
when that
problem is the
point is,
denominator is going to 0, but then I
and
observe that
yes,
x minus 1
Right.
times x minus 2 divided by x minus 1, and I can cancel this because when I'm taking the limit, you want to observe the behavior around that point, not at that point.
yes,
So
yes,
around that point, this cancellation is valid. Similarly,
right,
around this point, this cancellation is valid. So
makes
when
sense.
you're going from in a neighborhood of 0, 0, at 0, 0, you don't know what's happening. But at every point other than the 0, 0 in the neighborhood, the value is 1. So the limiting value
Right,
is 1.
makes sense. Yes, sir.
So the
Well,
limit exists.
here these points will be problematic, like if x is equal to 0 and y is equal to 0. But even that you can take care of. Like through any curve, it will still be 1 only.
Right. So basically, this curve is one except for the points where x and y are 0. If x and y are 0, it's not 1. That's the
Right.
kind of
If either
measure.
of x or y are 0, then this
0,
would
then
be a
it's
problem.
not 1.
Yeah.
Right, sir. Got it.
Well, if you talk about the limit of the function xy by xy, for example, as so, you would have to talk about something like this, where you're saying f of xy is xy by xy at where x is equal to not equal to 0 and y is not.
Right.
But what about the other points? So if you want to calculate the limit of some function, you have to give the values in a neighborhood of that function. So this
Yes, sir.
expression does not have values in the
It does
coordinate
not
axis.
exist on the domain, no, sir. It does not.
It does not exist in the neighborhood of the point for which you're taking the limit. So this thing doesn't make sense if only this is given. If it is given that, well, it is 1 at the axis, I'm just going to write at the axis,
Huh.
then you'll have the axis minus maybe origin. So if you want to calculate the limit of a function at a given point, you need to know the value of the function at every point other than the point of interest around that point.
Okay. Got it, sir. Sir, but I did not understand the last piecewise function that you wrote. What was the motivation behind it? I did not understand that part. Sir.
Okay, so if you okay, fine. Let me just do this. If you want to say that I want to find the limit of this function xy by xy, is this something like that? Is what you are saying, right?
Yes, sir.
As xy goes to 0 0, if I want this symbol to make sense, I need to know
Right.
the value of the thing that I'm taking the limit of in a neighborhood of 0 0.
Right.
But whatever small neighborhood of 0 0 you take, there will be points which are on the coordinate axis, to be precise, where this function is not defined. So this function is not defined in a neighborhood of 0.
Right. So the limit does not exist, sir, but you said
No,
it's one.
it does not make sense to talk about the limit. So that's why you have to specify what it is on the axis also.
Okay, so in this case, because in the definition you mentioned that all curves passing through the point must converge at that point, right?
Yeah,
So,
so
but
this is a
here the
function. Domain of this is R2 minus the axis.
right, then it would be one.
No. The domain of this function is R2 minus the axis, right? So if you look at the domain, it will be everything other than the axis. So it's this, and this.
This,
There are like
yes,
four
yes, sir.
disconnected components. And you
Yes,
cannot calculate, it does not make sense to talk about the limit of the function when your neighborhood of the point does not contain, there is no neighborhood of the point which is contained in a domain. So you can
right.
take a limit of a function only at a point which is in the interior. I think you should go back and look at the Prox videos where he talks about the function exists in a neighborhood of the point. So in this case, xy by xy does not exist in the neighborhood of 0 0. So it does not make sense to talk about limit xy as xy goes to 0 0.
Okay, so in this case, the answer is that does not exist because the axis is in the if we go to the axis's direction, the limit does not exist.
I'm not saying the limit does not exist. I'm saying that it does not make sense to talk about the limit. So this, whenever you say limit as x tilde goes to a tilde of a function f
Right.
of x tilde in general, this a tilde should be a point such that in a neighborhood of a tilde, f is well defined. Only
Right.
then this symbol itself makes sense. But in a
Okay.
neighborhood of 0 0 0, xy by xy is not well defined. This is sort of very the rigorous side of mathematics.
Right.
You are understanding what I'm saying, right?
I understood, sir. Here we do. It
Yeah.
doesn't make sense to even put that limit symbol because
Yeah.
we it. I got that, sir. Got it. But why I asked this question? I just came up with this in my mind because I just wanted to confirm, like we cancel things out in traditional,
In
what do you call one variable calculus.
okay.
We
Okay,
can do
if you
that
do
here also.
instead of this, if you have this is
Yes,
a
sir. Yes,
less
sir.
problematic
Something. Yeah.
example because this
Yes.
exists in the neighborhood.
Yes, sir.
It only
Yes.
when it only doesn't make sense at the origin.
Right. Right, sir.
Everywhere
So
else it makes
here,
sense. So here
here
this
it
is
will
one.
pakka would be one. Makes sense. Right,
Yeah.
sir. Got it. Sir, so the statement where all curves are passing through a point. Suppose we have a three R3 to R. Would it be all planes passing, or would it still be all
No,
curves?
it'll still be all curves.
Got it, sir. Got it.
So,
And
sir,
sir,
Because
right. Yes, sir. You're telling, sir, the reason.
the planes thing, I'm saying that doesn't make sense because yeah, you're looking at like sequence of points going to
Ah,
the point. So that is
okay,
still
sir.
along the curve.
Along the curve. Got it, sir. And
Yeah.
got it, sir.
so what is the difference between the two functions? The one which we did before, that is xy by xy, and this one.
So okay, if I do this, this is something that is not defined in the neighborhood of the origin, is what I'm saying. Why is it not defined in the neighborhood of the origin? Any neighborhood of the origin, it would look like something like this, and there will be points of the x-axis and the y-axis as a part of the neighborhood, and on
Yes.
that, this expression doesn't make sense.
Okay. So
Okay,
how
but
did we conclude that it doesn't make sense, and for one and for other it makes sense?
so
That
if
is
I take some small point, like something like delta comma 0, this is a point on the x-axis. If I substitute it over here, it doesn't make sense. No, it would be 0 by 0, which is an indeterminate
yes,
form.
sir.
So some such point will always be there, irrespective of what small neighborhood you take. You
Mm-hmm.
will have some point of the form delta comma 0 in your neighborhood.
Okay. Yes, sir. Got it.
So
Got it.
in that point, this function would not be well defined.
Yes, sir.
Whereas this one doesn't have that problem because even if it is delta comma 0, there will
Yeah.
be delta square plus 0 by delta square plus 0. This delta is
Yes.
not 0.
Yes, sir.
This
Yes, sir.
function is only not defined at the point, and that is
Okay.
okay.
Yes, sir. Yes, sir. Got it. Got it.
Sir, one last question, sir. How do we know if a plane exists or not? What is like the computational method to see if a plane exists or not?
Well, a sufficient condition again is well, it is actually yeah, it is just a sufficient condition. Partial derivatives exist and continuous. That would be enough. But partial
Okay, sir.
derivatives. So even in this case, you will see that the partial derivatives are not continuous. So in this case, if you're traveling in the x direction at this point, the partial derivatives over here will be in this slope, and over here it will be in this slope. So that's not continuous, right? It's like it's going from
Right.
-1 to +1 in some sense.
Right. Yes, sir. Yes, sir. And if we
So
travel in the y direction, the partial derivative is always constant.
it's zero.
Zero. Yes, sir. Zero.
It's constant. It's like constant. Well,
Right, sir.
partial derivative. There, z value is not changing. So there it will be zero. But in the x direction, it is traveling constantly in one direction, and
Right,
then
sir.
suddenly it turns around. So that is another way of looking at what is a fold or what is a sharp edge,
Yes, sir. Makes sense.
where your partial derivative, it was traveling like this and suddenly it travels like this.
Right, sir. So when we say partial derivative is exists and continuous, we mean that the limit exists and it is continuous in the neighborhood. Correct, no, sir?
Yes, yes. So this fx is a function. You know what continuity of a
Yes.
function is. This is continuous and
Okay.
this is continuous.
So the function must be continuous at that point. Got it, sir.
Yes, yes,
So that function should exist and should be continuous.
yes.
So the
Got
limit
it.
has the limit has to exist for continuity, right? Then only it will be
Yeah,
continuous.
yeah. The corresponding limit has to exist. So
Yes.
in this case, if you take a curve like this, the limit will be different from a curve like this. If you take a curve on the other side of the sheet, if you take this curve,
Correct, correct.
right? So
Yes.
all of this is difficult to explain
Understood.
on paper, but hopefully, yeah, you
So
got
in
it.
so in basically the limit for continuity, the criteria is the limit has to exist for the function. Basically.
Continuity, yes, yes. But once again, verifying whether the limit of a multivariable function exists is not easy. Then you'll have to use something like sandwich theorem to prove that the limit exists. To prove it, to say that it does not exist, it is easy. You can take a particular sequence, smart choice of two lines. If they give different values,
Yeah.
you can say continuity is failing or the limit does not exist.
Understood. In some functions,
Yeah.
like if they are giving different values, understood.
Right.
And
If you
when,
take y is equal to x and y is equal to minus x, for example, in that question that I was saying earlier, where was it? Yeah, this guy. In this, if you take y is equal to x, y is equal to minus x, you'll get different answers.
yeah.
So the
So
limit
if
at
we
0, 0 does not exist.
so basically, if we approach from different curves, it should give the same value basically.
Yes. And lines are not sufficient. You should take all possible curves.
Y equal
There
to
are
mx
functions.
equal to mx square and all those things we'll have to take.
Yes, but there is no exhaustive list, no? Even polynomials are infinite. That is why if you want to actually prove, you'll have to use something like
Yes.
sandwich principle.
Okay.
Got it.
And there is no
Sir,
short way of algorithmic way of doing that. You'll have to look at the function and decide upon how you will pinch it or whatever.
got it, sir. Sir, a sphere would not, if there's a sphere which has a center around the origin, this is not a multivariable function because there are multiple points if we, like that horizontal line test kind of thing.
Okay, so if you have a sphere, this is not the graph of a function, is what you're saying.
Yes. No, I'm just asking, sir, if there's like a sphere
Yeah,
and suppose
it's not the graph of a function because the height at every point has to be unique. No, so here you have this and this.
Got it, sir. So the
So
same kind
only
of
a
principles that apply in
hemisphere would
simulating.
be.
Yes, sir. This would be. Yes,
Yeah,
sir.
this would be. So this
Got
would
it,
be
sir.
what? This would exactly be. Suppose this is a sphere of radius 1. Any point on this would be something like x, y, z, such that x square plus y square plus z square is equal to 1. I'm just giving a little bit of extra stuff. This is really not necessary. But I'm telling you what happens, what is the problem that happens in the case of sphere and how it is circumvented in this case of a hemisphere. If z square is equal to 1 minus x square minus y square, if you want to write this as a graph, you have to write it as z is equal to something, right? That is the graph of a function. But if you
Yes.
take a square root, there are two values, plus or minus. So that's why the sphere itself, the whole sphere itself does not become a graph. But if I take one choice, which is plus, I'll get the upper hemisphere. This is upper
And
hemisphere.
minus below hemisphere.
Minus will be the lower hemisphere.
Down lower hemisphere. Yes.
So both of these are graphs, but the sphere itself is not a graph.
Got it, sir. Makes sense.
Okay.
Sir,
I think now we have to go.
Sure, sir. Thank you for your help, sir. Thank you.
Yeah, if it is quick, just let me know where we can.
Sir, what is next?
That's it, sir. I mean,
That's it.
Okay. All right.
Thank you.
Any other doubts?
Sir, class will be going on.
No, it's done. Unless you have doubts, it's done.
Sir, if we could scroll something above from the like little bit of stuffs.